Swayam Prabha. Digital India. Educated India.
Alright, good morning, good afternoon. Welcome back to our series of lectures on analysis and design of rigid pavements. In this class, and we're almost through with almost the entire class, we actually have very few lectures left. We have covered a large number of topics on the analysis and design of rigid pavements. Just as a quick refresh to what we've covered, way back in lecture 1 or module 1, which was actually first 4 lectures, we actually had an introduction. But I told you there are 4 different types of rigid pavements. We talked about what are rigid pavements, why they're important, and then we finally came down to what are the 4 types of rigid pavements. JPCP, jointed plain concrete pavements, JRCP, jointed reinforced concrete pavements, CRCP, continuously reinforced concrete pavements, and PCP, pre-stressed concrete pavements. I had mentioned that JRCP and PCP, we are not going to talk about it in this class. They're either very rare or highly specialized. JPCP is by far the most commonly used type of rigid pavement. CRCP is also fairly used. It's certainly not as widely used as JPCP, but it is fairly used. And then one of the important things we talked about in module 1 was distresses. In particular, what are distresses that we expect in rigid pavements? How do we measure them? How do we quantify them? So I mentioned in JPCP, we are basically interested mostly in cracking, which is fatigue cracking, which is sometimes also called transverse cracking. So we are basically interested in cracking, and we are also interested in faulting. For CRCP, we are interested in crack width, we are interested in crack spacing, and we are interested primarily in punch-outs. That's the primary failure mechanism that we observe in CRCP. Now, what I had talked, we had then spent module 2 and module 3 on analysis. Why did we spend so much time on analysis? It's because mechanistic empirical design, which is the modern theory of pavement design. Mechanistic empirical design is basically an iterative process. You choose some design, some trial design. You perform an analysis. From the analysis, then you added reliability. And that's reliability is what we talked about in the previous lecture. I explained why do we need it, how do we use it, how does it affect our design. I had mentioned all of those in the previous lecture. So you may just want to go back and review that for a moment. But I had talked about reliability, and then based on reliability, we judge whether a pavement is predicted to perform adequately. What is adequate is really a policy decision. Are you okay with 10% slabs cracked? Are you okay with 0.1 mm faulting, etc.? So that it's a question for the policy decision. That's not really an engineering question. So we are interested in a particular threshold. So if our predicted cracking is less than what we are okay with, that's a good design. If not, we have to go back. We have to update our trial design, and we have to repeat the analysis. So clearly, it's very important to be able to do the analysis. We saw how we did analysis using classical methods. So classical methods are closed form solutions. They basically give us nice closed form solutions. They do solve a partial differential equation, which is the Sophie-Germain equation with a correction factor added in to account for the Winkler foundation. So it is that partial differential equation which, under a series of assumptions, some very smart people solved in the past. Similarly, for dowels, it's basically based on beam theory. For dowels, then we had the Freiberg solution. And the Freiberg solution then told us how to analyze not just one dowel, but a system of dowels. But then we also saw that, well, the advantage of these analytical methods was we got some nice equations. We actually took some time to solve several problems, and we saw that it was a fairly nice thing that we could do. As long as we were careful about doing proper calculations, we were particularly careful about units, which is something we'll come back to in a couple of lectures from now. But as long as we're careful about units, as long as we're careful about our calculations, we don't really need to know any specialized computer programming. You could do it by hand. That's a little tough. You could do it with a calculator. And that's typically how most students do it. You could do it on a spreadsheet in Microsoft Excel or LibreCalc or something of that sort. And that's in practice how it is done, if it is done in practice. So, but we saw that there are many problems with these analytical methods. One of the biggest problems is the assumption of an infinite slab. That it is assumed that wherever the load is, if there is a joint near that, it's going to affect the structural response, stress, strain, deflection. So it's going to affect the structural response, but the other joints are assumed to be very far away. So for example, if the load is placed, let me draw it here, if the load is placed in the middle of the slab, we just assume the joints are very far away from the load. Or if the load is placed at one of the corners, it's assumed the other two joints are very far away from this corner. That was one of the major assumptions. There are a couple of other assumptions also which is made, but that was one of the biggest assumptions which is made in this the classical methods. And as we saw, those can lead to some significantly erroneous results. And that's really why, along with the development of computers, in the last 90 years, in the last 30 years, starting from the 1990s, a lot of pavement design has more or less abandoned the use of these analytical solutions. Despite their historic value, which is why we learned it, most design methods have abandoned these analysis methods. Instead, we are now using the finite element method. So, generally we use numerical methods, and in this application, the finite element method is the most widely used. So, the biggest advantage of the finite element method is that while it's certainly very difficult to solve partial differential equations, and if you've taken a class on PD, you will agree with me, it's not the easiest thing to solve, particularly if the boundary conditions can be complicated. But the finite element method has the advantage that it converts the partial differential equation into a series of algebraic equations. Now, I don't mean 2 or 3 equations, it's a lot of equations. We'll have tens of thousands, lakhs of equations. So, it's a lot of equations, but nonetheless, we can solve it on a computer. So, the advantage of the finite element method is we don't actually have to implement anything by hand. Existing programs, and one we looked at was IceLab, existing programs exist which will do a lot of the calculations for us. The challenge with the finite element method, well, firstly, the basic assumption of the finite element method is that our solution is going to be wrong. We are incorporating an error on purpose into the solution. And we hope that the error is small. We hope that we can make it small by increasing the number of finite elements. So that's one shortcoming, but in practice, that's not a very big shortcoming. The other shortcoming is basically the maths gets quite complicated. You'll agree with me, if we go back to module 3 and you see all the mathematics we did, it was a fairly complicated thing that had to be done. It was not always easy, and even I had to do a lot of hand waving. Truly speaking, FEM is not something you can learn in 2 or 3 lectures. You have to take a full-fledged detailed course on it, and I recommend all of you, particularly if you have a civil or mechanical background, I recommend you to take such a course. Anyway, the good news for us as pavement engineers is there are ready-made programs out there which can do that calculation. In particular, what we've been looking at in module 4 is the mechanistic empirical pavement design guide. So that is one implementation of a mechanistic empirical design philosophy, probably the most advanced implementation today. So we've seen how the MEPDG, the mechanistic empirical pavement design guide, how the fact that it actually does all the computations for you. So if you use the pavement design guide, they have a neural network, they've done all the computations. So despite the fact that FEM being so mathematically intense, in practice, as practicing engineers, we don't actually have to do the calculations. A computer program is going to do the calculations. But yes, you do need to have that program with you. Okay, so we've been talking for several lectures now in module 3 on the first one, mechanistic empirical design as a philosophy of design. I told you there are basically 3 philosophies of pavement design. That is empirical design, that has been, say, from World War II until the 1990s, that was basically the leading type of design. And even today, most of the world actually still follows the empirical design. They were based on these massive road tests, the Asher road test, the Washer road test. They were based on these very, very massive road tests. Some of those road tests still happen today. There's a particular facility in Minnesota, for example, in the US, MinRoad. So that does these sort of tests, but they're very, very expensive. So instead, the mechanistic empirical philosophy, which is the leading philosophy today in India as well as in other parts of the world, the mechanistic empirical philosophy is to actually combine physics or mechanics, hence the term mechanistic. Combine or harness the power of mechanics to predict the structural response of the pavement under repeated loading. And repeated loading basically refers to that we're going to have to use fatigue theory. Fatigue theory was, by the way, not exactly used in empirical theory because it was not really based on much of a theory, but we use fatigue theory, and what we get out of this is we calculate fatigue damage. Now, fatigue, we could actually stop at that, but in mechanistic empirical philosophy, we claim that we don't really care about the fatigue damage. What we really care about is cracking, distress, basically distresses. So it could be cracking, it could be faulting, punch outs, crack width, etc. We really care about distresses. Now, if we could use physics to directly calculate the percentage of cracking, then that philosophy would be called a fully mechanistic design principle. Well, the problem is cracking by definition is a non-linear process, and generally non-linear mechanics is not easy to do. So even if some researchers could do it in their office or do it for a research paper, in practice, for a practicing engineer to be solving non-linear mechanics day in and day out is, at least today, it's somewhat unfeasible. So that's why between a purely empirical design and a purely mechanistic design, you have mechanistic empirical design in between. The idea of the mechanistic empirical design, we calculate a mechanistic response of the pavement under repeated loading, and that mechanistic response is basically the fatigue damage. We calculate the fatigue damage, and then we use an empirical function, a function which has been created using observations on active roadways. We use an empirical function which is called a transfer function to convert the fatigue damage to some kind of distress that we're interested in. That is the overall philosophy of mechanistic empirical design. We'll talk a little bit more today in comparing mechanistic empirical design philosophy and empirical design philosophy, but that's the general idea. So what are we going to talk about today? We're going to talk about a topic called design optimization. Now, in lecture 32, the previous lecture, which was on reliability, I had just told you that in the process of mechanistic empirical design, we come up with a trial section, we do a whole bunch of calculations, we add a reliability to it, and we saw the effect of reliability, and then we compare the predicted distress at that level of reliability to some threshold. And I said that if it exceeds that threshold, that means if the performance is not adequate for the trial section, we have to go back and update the trial section. I've actually shown that same figure, and I'll show it today also. I've shown that figure in several graphs, but I've never actually told you how do we actually update the trial section. What is the update that we have to do, and what are the options we have to make those updates. So today's lecture, lecture 33, is actually going to go into that particular aspect, which I've on purpose avoided for most of the lectures, which is on design optimization. How are we actually updating the trial section to get an optimized design? So, in today's lecture, I'm going to explain the concept of sensitivity, and particularly we're going to look at the sensitivity of the Pavement ME, or the Mechanistic Empirical Pavement Design Guide program. I'm then going to explain briefly how Pavement ME optimizes design, and as we'll see, it's actually fairly disappointing relative to the amount of sophistication which is available in the mechanistic modeling in Pavement ME. The optimization is actually not very sophisticated at all. So I'll explain to you what that is, and then I'll show you how, if we had the availability, and we'll actually see why the shortcomings are. I'm not saying Pavement ME is disappointing in the sense it's using a very simplistic optimization method. It's the best for what it can do. And so what we'll see is what are the challenges in doing more sophisticated optimizations, and how can we overcome those challenges. So that's going to be the topic of today's lecture. I will talk a little bit about research papers. I'll show you 2 research papers also. So it's a little bit more on a research topic over here. But I thought it's a good thing for you to know a little bit more advanced work than what's purely just in the documentation for MEPDG. Okay, so recall the ME design process. This figure I've been showing many times. It's something, well, I'm not saying you have to commit this figure to memory, but it's something you should be able to describe in very, very clear and succinct details. So that's why I keep coming back to it. So the general process of an ME design is we start with some inputs of a trial structure. So we choose some materials. We choose, say, M40 concrete. We choose certain type of aggregates. We choose maybe a DLC, a dry lean concrete layer, etc. We choose some materials and we choose some trial thicknesses for those materials. We have to choose some design value of traffic. Again, the problem in design is that there is no road and therefore there's no traffic. So we have to use our judgment to choose some value of traffic that could be good or bad, but it's on us to decide what that judgment is. We have to decide certain properties related to climate. Here again, there's a fair amount of variability. We might have several choices in terms of how we want to characterize the climate of a location. We have to see which one we want to work with. We also have to consider some amount of variability. Generally, this variability could be, for example, FCK, so the characteristic strength. So we don't use the mean compressive strength, we use the characteristic compressive strength of concrete. This could be one example of where variability is being incorporated into the trial structure. From there, then we calculate structural responses using a mechanistic model, using a mechanics-based model. Structural responses are basically stress, strain, and displacement. That's what we mean by structural responses in a linear elastic sense. And then these structural responses, which are mechanistic in nature, they of course then get converted into fatigue damage, or they might be converted to differential energy. So it's taking into account the theory of fatigue. We have to do a little bit more work, but we get some value, which is a purely mechanistic value. The mechanistic value then has to go into a transfer function, and the transfer function is purely empirical in nature. The transfer function is going to give us, the output of the transfer function is going to be a distress. So for every distress, there is a transfer function, and indeed there are many transfer functions. They are empirically made, so there are new transfer functions basically being created all the time. So for cracking, you'll have a different transfer function, and even for cracking, you'll have a variety of different transfer functions, so on. So what we saw in the last class was we get this distress as an output of the transfer function, and to that we have to incorporate reliability. And what we saw is the way we incorporate reliability, say our transfer function gives us the output x. That is, in our assumption, we assume this is at a reliability of 50%. We saw that in some cases, maybe 50% is okay, but certainly for highways and expressways, you expect a much higher level of reliability. So then we saw that if we wanted to get reliability at some reliability R, we actually have to take the predicted value out of the transfer function x. So this x is going to come out of this transfer function, and we have to multiply it by some z-score, which is relatively easy to calculate if it's a normal distribution. And for distresses, we talked about central limit theorem last time, and we said it is generally a normal distribution. So please go back to the previous lecture and review it if some of this stuff seems a little fuzzy to you. So this is x plus zr into sigma, where this sigma is some standard deviation, and we saw that sigma is generally also going to be a function of x, and this is an empirical function which has been created. So this reliability is added, and this xr is then going into the next box, which is pavement performance compared to failure criteria. So we see, is xr less than or equal to some failure criteria x. So this could be, for example, the failure criteria x could be the percentage of slabs cracked, that is transverse cracking. Maybe the required value or the maximum threshold is, say, 20%. It depends on the road, it's an agency decision. But let's say it's 20%, and let's say let's say 90% or whatever percentage of reliability, the predicted cracking, so let's say this is 20% over here, and the predicted cracking turns out to be 27%. We saw this example last time. Well, clearly 27 is not less than 20. So we say this design has failed. We have to then go back. We have to update our trial structure, and this is going to be the main part of today's lecture. Somehow we are going to have to create a new trial structure which we hope will work. Continue this process until this passes, until our XR is less than or equal to capital X, that is until our predicted distress is less than our maximum acceptable value or threshold value for the distress. We keep updating our trial structure, we keep repeating the analysis until we reach this point. Once we reach the point, whatever design we get, we call that the final design. So the only property of the final design is that the predicted distress is less than the maximum allowable value of the distress. That's basically what we hope to get from our final design. So how is this different? This was the mechanistic empirical design process. How is this different from empirical design? Is it not the same process in empirical design? Actually, no, it's a very different process in empirical design. Empirical design basically provides us as a thickness as an output. So in empirical design, we have a series of inputs. So we have climate input, we have material input, we have traffic input. And what the procedure does is it tries to tell us what is the thickness of the JPCP or whatever layer, what is the thickness of the layer required such that the pavement will perform well or such that the pavement works. What is works? Whatever it was based on during the road test. So in the road test, if they actually if they tested a large number of sections and they put a lot of loads, and in the road test, if they decided, well, I want 30% cracking or 20% cracking, then that's going to be a section that works. So then what you do in empirical design is it will just try to get you as close to that section which was built during the road test. So let's say there was a section in a road test for a particular combination of traffic and climate. Let's say it had a 300 mm slab, which is a JPCP slab. And it was found that it was designated to be an okay section, that it worked adequately, whatever adequately meant back then. Now what will happen is in empirical design, if you have a similar set of inputs, so you have similar climate, similar variability, similar material as for the load test, we hope that whatever equations come in an empirical function, it will similarly give us around 300 mm thickness for the layer. That is because this worked in the empirical design, the empirical test, that's what the design should give us. So in empirical design simply provides the thickness as an output. You get one value as the output, that's it. There's nothing more that you have to do. The principle here is to get a design that just works, or rather a design that happened to work. So you want to get as close as possible to a design that happened to work in the past. That is not what happens in mechanistic empirical design. ME design is actually very, very different philosophically. ME design takes a large number of inputs. So in empirical design, we didn't really talk about Astro 93 empirical design much here. So just believe me on this phrase. Empirical design takes a very small number of inputs. A handful of inputs, 5 or 6, relatively easy to solve by hand, because in the 1950s and 60s when it was developed, you actually had to solve it by hand. So it takes a large number of inputs. More ME design, on the other hand, because by the time ME design came up, computers were available. So it takes a much larger number of inputs, and of course, a computer is going to deal with those inputs, not us, including thickness. Now, this is the big deviation between empirical design and mechanistic empirical design. In empirical design, thickness is the output. In mechanistic empirical design, thickness is one of the inputs. So we can choose a thickness. Indeed, we have to specify some trial thickness to start with. And then what ME design does, based on all these inputs, including a trial thickness, it's going to calculate the fatigue damage and from there distress. So that's basically exactly what I showed in this figure. Key here, however, is the principle is to predict performance. So the principle of the empirical design is to just get a thickness or a design that worked in the test section, whatever worked mean as they defined it in the test section. The principle of mechanistic empirical design is to directly calculate performance. That is, decide how much cracking do you expect, how much faulting, how much punch outs, etc. Decide that value, predict that value, and then let the user judge if it is acceptable. So, for example, the philosophy in empirical design would be, given some traffic, climate, given some material properties, here is the thickness of the JPCP section to use. The philosophy in mechanistic empirical design is, given some trial sections, so given some traffic which you reasonably expect, given some climate which you reasonably expect, given some material properties, and given some thicknesses of the layers. That's a very big distinction. Given some thicknesses of the layers, it's not telling you whether it works or not. It will tell you the program predicts 10 or 20% crack. Whether that's sufficient or not is left up to the user. So as you can clearly see, philosophically, these two are very different. Empirical design is giving us one answer and only one answer. Mechanistic empirical design gives us an output of performance. Whether it's an acceptable design or not is for us to decide. So in the AASHTO 93 design guide, which is the empirical, so the AASHTO 93 was basically the empirical guide. In the empirical design guide, we get one design section. In the AASHTO pavement ME, or in general in ME design, we develop design sections that satisfy performance criteria. That is, we try a variety of sections and we try to get a section which satisfies the performance criteria. Cracking is less than so much, faulting is less than so much. What is key to understand, many such sections are possible. So in the empirical design guide, you will get a unique answer. You will get one design out of it once you flow through the process. In mechanistic empirical design guide, you can get a variety of solutions. It is not necessary for a given set of inputs, for a given set of material properties, etc. It is not necessary that you will always get a unique answer. Depending on how you do your updates, and that's the subject of today's lecture, depending on how you choose to update your trial section, you can actually get a different design that works. And so you do not get a unique design, you actually get a variety of designs, all of which might satisfy the criteria. So just to give you a concrete example of how this might work, maybe one of your strategies to update. So again, here, when we update our design, maybe one of your strategies to update was just to increase the thickness of the JPCP. Leave everything the same, increase the thickness of the JPCP. You will get a solution that works. Another strategy could be, leave the JPCP where it is, increase the thickness of the aggregate layers. You most likely will eventually get a section that works. Another strategy could be, don't change the thicknesses. Instead, choose a higher grade or higher flexural or compressive strength of the concrete. So instead of using M40, use M45, use M50, for example. You will also get a design that works in that case. So as you see, in the empirical guide, you'll get one answer. In the mechanistic empirical guide, depending on how you choose to update your design, you can get a variety of different answers. Okay, so this function that we have, we basically want to minimize the function. We want the predicted distress to be as close to the maximum allowable distress as possible. How can we achieve that? We can change any of the input variables. We can change the thickness, we can change the material properties, we can change the type of materials that we're using. For example, we could go from a granular base to a cement treated base. So we have all these variety of options. We may also have some conditions. For example, we do require the thicknesses to be positive, quite obvious. but we could say the thickness should not be less than some value. For example, for practical reasons, it might be very difficult to construct a JPCP layer which is less than 100 millimeters thick. You get into trouble with the size, maximum size of the aggregate, etc. So it might be difficult to construct if you're getting below 100 mm. So we might put some limits on what are the values of the inputs that are physically going to be allowable. This is basically an optimization problem. To put in a little bit formalized terms, this function f, that is the function that we want to minimize, this function f is called an objective function. The objective function is a function of, well, it's of predicted distress. The predicted distress is a function of a number of input variables. So these are what we call the input variables, or sometimes we call these the independent variables. Let me write that down. So these are the independent variables. So we have an objective function, which is a function of several independent variables that we can vary. And we want to minimize this function. We want to choose some values of these independent variables, which minimizes the objective function. But we are subjecting it to certain what are called constraints. So these are what we call constraints. So we are subjecting this to certain constraints. That is, we are not allowing any value of the independent variables. We are constraining the values of the independent variables. Within those constraint values, we want to find a solution which minimizes the objective function. This is basically what we call an optimization problem. And as you can probably relate to it, if you think about it, how is this related to JPCP design? You'll probably see that it is fairly close. What are we doing in JPCP design? What are our independent variables? Thickness, material properties, type of materials, etc. So those are our independent variables. Our predicted distress is what we've been talking about so far. That's what comes out of a mechanistic empirical design, predicted distress. Allowable distress is whatever we get, as a policy we choose. And of course, we have a reliability also built into that. And constraints are the physical constraints that I mentioned. Thickness cannot be too low, it cannot be too high, etc. So this is basically what we are trying to do in any optimization process, but particularly in this mechanistic empirical design process for rigid pavements. We are trying to minimize the difference between the maximum allowable distress to the predicted distress and choose a series of inputs, but within reasonable values. We are choosing a series of inputs within some constraints that satisfies this condition. Now, what happens is you can have many such conditions. You can have many different solutions such that you get a minimum value of this. All of them are said to be called local minima. So here again, this answers the question what I wrote here. Why is it called a minima? Is basically we're trying to minimize this objective function. You can have many different trial solutions that can minimize this function. We call all of them a local minima, but we call one of them, that is the one with the minimum of the minima. That solution which has the minimum value of the local minima is what we call a global minima. That is the difference between the maximum allowable stress and the predicted stress is the smallest for the global minima. There are other values where it is also small. Those are what we call local minima. The holy grail, or what we really want in a design optimization, is can we get a global minima? That is, across all possible designs, across all possible variables, can we get that one combination which gives us the absolute least difference between predicted distress and the maximum allowable distress? That's called a global minima. That's what we would like to get. But there are certain problems along the way. The space of all possible solutions that create at least a local minima includes all the input variables. So if we had the choice to freely change all the variables, how many variables do we have in design? We actually have well over 50 input variables. So you have the choice of choosing a very, very large number of values across 50 different variables. Mathematically, this very quickly becomes intractable. The number of different combinations that you would have to look at, the number of different combinations that you have to design would go into trillions. It would not be possible to actually do this. There are basically so many local minima that you would have a very hard time evaluating the global minima. So what do we do? Well, one approach is to reduce the design space. That is, okay, we know that we have well over 50 input variables, but maybe we know through some analysis, and I'll actually show you the analysis in the next slide. Through some analysis, maybe we know that all those variables are not that important. Maybe we know that the distress, what we're concerned with, the distress is particularly sensitive to a handful of variables, such that if we just slightly tweak those handful of variables, we can significantly reduce the distress. If we know this, and there are other variables where even if we make a change to the value, maybe the distress is not going to change much. We can call those the insensitive variables. So if we can classify variables as being sensitive and non-sensitive, that is, the distress is sensitive to some variables and not so sensitive to other variables. If we can classify our independent variables accordingly, then we might just choose some fixed values of the non-sensitive variables, since the distress doesn't really strongly depend on what the choice is. We might choose not to optimize for the non-sensitive variables. We might just keep them aside, and we choose to only optimize for the sensitive variables. What that's going to do is, instead of having to consider 50 variables and becoming a very mathematically intractable problem, we basically reduce the design space. We reduce the number of variables considered only to a small handful of the really important variables. This process has been done in the past. In fact, this issue of the fact that you have such a large design space that it's almost impossible to get the global minima, this thing has been considered in the last 2 decades. So this particular report I'm going to show you, this is the same project actually that created the MEPDG. So if you remember, MEPDG was the report 147A, this was 147FR. So this is another report which is from the same project, titled Sensitivity Evaluation of MEPDG Performance Prediction. So I think the name itself says everything. MEPDG Performance Prediction, that's what we're talking about. Sensitivity Evaluation. How sensitive is the performance of the JPCP section as predicted by MEPDG to its independent design values? So what they did in this study was, the challenge in sensitivity, so they basically took a number of inputs, they varied the inputs, and they saw how did the output, namely the distresses, how much did the output change accordingly. So for example, if I double the thickness, how much do I change the cracking? Is the cracking halving, or is the cracking becoming 1/4, 1/10, etc.? That's basically what they were trying to look at. Now, a challenge of course which exists is that you have a variety of inputs and you can try a variety of combination of these inputs. A challenge with sensitivity analysis is actually to ensure that whatever cases are being analyzed are actually realistic. What is an example of an unrealistic case? An example of an unrealistic case could be that if we have a section which has heavy traffic and we choose a very thin pavement section, we can run our software in order to calculate the distresses, but in practice we would never ever design such a thing. So one thing that has to be done in sensitivity analysis, you should not do every possible combination of the variables. You should filter out the combinations to only those which are realistic combinations. So for example, what are the different combinations they considered in this particular report? They basically looked at 3 different types of inputs. So they looked at pavement type, so that could be a flexible pavement and rigid pavement, both new as well as reconstructed. They looked at different types of climates. So they looked at hot, wet climate, hot, dry, cold, wet, cold, dry, and temperate climates. So this is again in the US, so they didn't really have the tropical climate that we have in India, but they looked at different types of climates. They also looked at 3 different traffic levels: low, moderate, and high. So these were sort of the overall cases that they looked at. And then within each, they considered a large number of design variables. Now, I will not be able to go through all the design variables. It's really a very large number. So I won't be able to go through all the design variables. What I wanted to show you is what are some of the variables that they used for JPCP. They did not consider every possible one. So we had already said that there were around 50 different inputs which are possible. And indeed, if you really start pushing it, that is, you start containing if you start assuming even the calibration coefficients in the transfer function, even those can be varied, you can start easily getting above 100 different variables. That's not what is done in practice. What is done in practice is they basically chose this handful, I didn't count this, but they basically chose a handful of properties. It's still a very large number. Handful of inputs which they believe, through their insight, through their experience, they believe that these are probably the most important variables that should be measured. So first of all, starting from all the possible 50 variables, they cut it down based on their experience to a smaller number, just so that the sensitivity analysis also doesn't take forever to perform. What are some of these inputs? One input was the construction month. Why does the construction month matter? It actually goes back to that built-in curling we talked about. Depending on the construction month, the amount of built-in curling, the amount of temperature stresses which are going to form are very different. If you construct the pavement in summer, you'll get different type of stresses being formed. Whereas if you construct the pavement, let's say in December or during the winter. So construction month was a value that they looked at. Another one, let's see, they looked at joint spacing. I think this is quite obvious. Size of the slab is going to affect the performance. It's going to affect the stress ratio, fatigue damage, and therefore performance. So they looked at that. Other values. They looked at the coefficient of thermal expansion. We didn't really look at this too much. We saw the coefficient of thermal expansion in a couple of our slides. We didn't go into a lot of details on calculating the strains, but the coefficient of thermal expansion is very important when we do climatic considerations. So they looked at how CTE, coefficient of thermal expansion, how sensitive are the results to coefficient of thermal expansion. Let's see, they looked at obviously the modulus of rupture, which we better know as the flexural strength. And then they also looked at, let's say, the resilient modulus of the base. They looked at the total depth of the entire pavement, which is called the cumulative depth. So, and they also looked at the groundwater depth. How deep is the groundwater? Because that affects the moisture in the granular layers. We had talked about moisture considerations in a lecture on EICM. You can go back a couple of lectures and review that. So, they selected these as what they believe are the important parameters. And then they chose 3 values of them: the baseline value, the minimum value, and the max value. So they chose a 1 value as a starting point, which is a reasonable value, and they then chose a lower value called the minimum value, and then a higher value, a maximum value. These are all based on experience. So for example, if we take, let's choose one, if we take the modulus of rupture. Now these units are in PSI, so the units vary a little bit, but I'll try to explain it to you. So when they chose modulus of rupture, they chose 620 PSI. That roughly corresponds to around 5 megapascal, what we generally use also. That's their starting point. And then they chose, okay, let's choose a value which is maybe 10% or 20% lower than that. That's the lower limit. And they chose another value which is maybe 10 or 20% higher than that. That's how they did it. So for each of these variables, they basically chose 3 different values of the inputs. That was for JPCP. Similarly, for CRCP, it's very similar what the inputs are for CRCP. One of the big differences is, as you see over here, steel depth and percentage of steel. So those are things you won't find in JPCP. Generally, the steel depth is fixed. The percentage of steel is more or less fixed in JPCP. So, but in CRCP, as we saw, it is this choice of steel depth severely has a strong impact on the crack width, and the crack width then has an impact on load transfer, which in turn affects the stresses developed, etc., all the way out to punch outs. So please review that lecture on CRCP design. It was only a couple of lectures ago, if you've forgotten any of this. But so most of the inputs are the same for CRCP, but the steel related thing, that's a relatively new input. Okay, so what did they do in this case? Again, here they chose a baseline value, they chose a minimum value and a maximum value. What they did was, it's called a Monte Carlo simulation. Now, some of you might have heard of Monte Carlo. It's basically related to gambling. What the idea here was that, so for each of these variables, let's say they had 20 or 25 variables, for each of them, they had a range of values from the minimum value to the maximum value and the baseline values. They basically did the following. They chose each variable among these 3 possible values, the baseline, minimum, and maximum. They at random chose a value. So for example, for construction month, they chose one of these 3 at random. The next one, the bar diameter, that is the diameter of the steel, they chose another value at random. So basically, they went through each row and they chose one value at random. Those all became the input into the mechanistic empirical pavement design guide, and then the whatever is the distress, so whether it's punch out or cracking or faulting, the distress was calculated. This was done again. Another random combination was decided. How many combinations can we possibly have? It's a pretty large number. So if we have 25 and each of them has 3 different possibilities, that's basically 3 raised to the power of 25 possibilities. Obviously, they didn't run these many cases. This would be far too many. They ran a reasonable number, it was several tens of thousands. They ran a reasonable number, and what they get out of that is they get a range of outputs. All other inputs, so any input which was not specified here or here, they were all kept fixed. So they only kept it to these roughly 20 to 25 different inputs. And so that is basically what a Monte Carlo simulation is. In your complete design space, which covers all possible values of all possible variables, that's 3 raised to the power of 25 different combinations, you randomly select several, but not such a large number. You randomly select a fairly large number of combinations and you look at the outputs. So this is called a Monte Carlo simulation. Okay, once you get the Monte Carlo simulation, they went on to define a particular value which is called the sensitivity. The sensitivity of a variable with respect to another variable is defined as follows. The sensitivity is basically the derivative of the variable with respect to the independent variable. So for example, if you're interested in cracking, the sensitivity of cracking with respect to let's say thickness, if y represents percentage cracking and x in this case represents thickness h, then the change in cracking for change in thickness, keeping all other values the same. That is, if all other values are fixed at a particular value, then just what is the variance of cracking with respect to one particular variable, that is called the sensitivity of that particular variable. So mathematically is defined as follows: the sensitivity of yj, so that's one of the predicted outputs, relative to xk, keeping all xk is one of the input variables that we're interested in, so that could be, for example, thickness, keeping all other variables fixed at some value I. That is what is called Sijk. Of course, this derivative then has to be approximated using a numerical value, so just use a numerical approximation. Not too important to understand how this is done, but this is basically how they calculate sensitivity. How do we interpret this sensitivity? They provide some guidance on that also. So the Sijk, this so-called sensitivity index, can be interpreted as the local percentage change in the model output caused by a given change in the model input at location I in the problem domain. Which again basically means if I change my thickness when everything else is the same, if I change my thickness, how much do I change my cracking, predicted cracking? That's basically what sensitivity of predicted cracking to thickness and this local percentage change, meaning when everything else is kept constant. For example, Sijk, if it's 0.5, it implies that a 20% change in the local value of xki, that may be a 20% change of thickness, will cause a 10% change in yji. That is basically 10 over 20. So a 20% change in the input variable causes a 10% change in the output variable. That basically means the sensitivity is 0.5. So that's how you interpret the value of sensitivity. Of course, if the sensitivity is greater than 1, that is a 20% increase in thickness maybe leads to a 30 or 40% change in the cracking, then that would be a highly sensitive variable. So what they basically did at the end of this is, they calculated these sensitivity indexes and they classified, is the sensitivity index less than 1, which is to say it's not sensitive. That is, a large change in the input variable causes only a small change in the output variable. That they called as NS, or not sensitive. If the change was comparable, so if you double the input variable, you end up doubling the output variable, that's what they call roughly to be a sensitive variable. And then if you double the input variable and more than double the output variable, that is, you have a significantly large change in the output variable for a small change in the input variable, a relatively small change in the input variable, that situation is what they call very sensitive. So based on that, what I'm showing here is for JPCP, they actually went ahead and checked which of the variables, separately for faulting and separately for cracking, because it depends on the output. They stated here which is NS, not sensitive, which is S, sensitive, and which is VS, very sensitive. I'm not going to go through this entire list. You can do it yourself, but this report is free. You can download it and go through all the details yourself. For example, they found these, let me look at dowel spacing. Dowel spacing was found to be a not sensitive variable. That's a surprising result, but that's what they got. Basically, the cracking and faulting did not turn out to be a very strong function of dowel spacing. Whereas, if we consider joint spacing, width of the slab, both faulting and cracking were very sensitive to joint spacing. Another example, the granular base thickness. So if you're providing a granular base layer, the thickness of that, it was a sensitive variable. So it was not sensitive, it was not very sensitive, it was just somewhat sensitive. Or we could take another example, let's say the cement type 1, type 2 cement, etc. That was found to be a not sensitive variable. So in this way, all these around 20 to 25 variables that they started with, they classified them as not sensitive, sensitive, and very sensitive. They did the same thing, by the way, for CRCP. I'll leave it to you as an exercise to go through this and pick up values which you think were sensitive. Again, the main thing was the steel depth. Steel depth, surprisingly, for punch-outs turned out to be non-sensitive. That was an interesting finding. Okay, so the sensitivity index for each value of the distress design input combination, it was found it does not vary substantially with climate zone. So what they found is that all of whether the variable is sensitive or not sensitive or very sensitive, it more or less stayed the same across different climate zones. That's an interesting finding. One of their interesting findings was the PCC unit weight. So that's density into G would be called unit weight. The unit weight actually turned out to be quite a sensitive input. So the PCC unit weight is an important factor in the calculation of critical responses in rigid pavement structural model. It's basically the self weight of the slab. It was found that this is actually a fairly important value through its influence on curling deflections, namely faulting, as well as on transverse cracking. So, according to the authors then, so one finding was the sensitivity does not vary that much depending on which climate zone you're in. Another rather surprising finding was them that the sensitivity of the unit weight is fairly high. They did not expect that to be the case. I thought that should have been the case, but that was their finding. Interestingly, they found that PCC thickness is a relatively less sensitive input than PCC material properties. Now, that is a very, very interesting finding. I'm going to contrast it a bit in terms of finally what the MEPDG does. But you just want to remember this point. PCC thickness is a relatively less sensitive input than PCC material properties, which means it might be better not to change the thickness of the pavement of the PCC, but maybe increase the strength of the PCC. According to them, that's probably a better way if you want to decrease the cracking or if you want to decrease the faulting. I'll come back to this in a couple of slides. Okay, so what do we do with this? So this study was conducted. We start with all the 50 plus input variables that are taken by Pavement ME. If you want to do a full-fledged optimization across all these variables, it is very, very hard. It's too many variables basically to consider. Mathematically, it becomes an intractable problem. So we perform this sensitive analysis. We reduce the number of variables that we are interested in to a handful. In this case, maybe they got 10, 15 variables which were sensitive or very sensitive. Those are the only variables that really have to be considered. So based on this analysis, it is possible to limit the number of input variables to just a handful. For example, maybe, and this depends on the designer, maybe you'll say I'm only interested in the VS variables, the very sensitive variables. So I ignore the NS, I also ignore the sensitive variables. I'm only interested in the VS variables. I might be able to bring down the number of variables to maybe 5 to 10. It's a handful of variables that you can bring it down to. What you then do is you create a simplified model. In that simplified model, instead of giving the user the choice of all 50 plus variables, you only limit their choice to 5 to 10 variables that they have to develop for optimization. These simplified models are built on top of Pavement ME. So we are still using Pavement ME. We are using all the models and all the knowledge of Pavement ME. We are just reducing the number of variables that the user can change. These are what are called simplified models. This is actually a very, very active area in research. There are many researchers who are trying to develop more and more simplified variables, simplified models, all built on top of Pavement ME, so that they can come up with easier and more optimized designs. One of them which I wanted to show, which although I am not a co-author on this, I was associated with a later version of this work. So this is a paper called another tool which is developed. Let me read the title. So Pit Rigid ME, Simplified Mechanistic Empirical Design Tool for Pennsylvania Rigid Pavements Design Analysis. Pennsylvania is a state in the US. I lived there and worked there for some time. So this was a particular program called Pit Rigid ME. And this was published in a very good journal, the AC Journal of Transportation Engineering. I had mentioned in this lecture, I wanted to bring out a little bit more on the research side over here. That's why I'm taking you through this, just to show you the value of this. So what did these two researchers do? First thing, again, similar to the work from the NCHRP report which I just talked about, they also used Pavement ME and they chose a handful of variables that they thought would be important. They performed a Monte Carlo simulation and then they saw that after the Monte Carlo simulation, how much variation do we get in each of the outputs. Now, in this case, their output was actually the fatigue damage. And if you recall, we separately have a bottom-up fatigue damage and a top-down fatigue damage. So this is bottom-up and this is top-down. Let me write this here. So this is bottom-up and this is top-down. So what they saw, for example, let's say joint spacing. They chose a variety of values of joint spacing. They ran the program and they calculated what is the fatigue damage, both on the top-down and bottom-up cracking, what is the fatigue damage predicted. And they saw this quite a big range of fatigue damages being predicted. So as you change joint spacing, the range of fatigue damage is quite high. Whereas, let's pick up another variable. Here we have subgrade. So this is the choice of type of subgrade that they have. They didn't actually vary the K value, they varied the choice of subgrade. They saw that it's not actually that important. Whether it's top down or bottom up, it's not too important to be able to vary the type of subgrade. So in your design, you might just take whatever subgrade is available, subject to some minimum CBR. You don't want to spend too much time on that particular aspect of the design. Similarly, for other variables, I won't go over all of it. I'll leave it for you to read all of this on your own. But so over here, what they did was then they first of all, out of all the 50 plus possible inputs in Pavement ME, they chose a handful which they thought would be important. They performed the Monte Carlo simulation. I defined already what is a Monte Carlo simulation. They performed a Monte Carlo simulation and then they found which variables are particularly important, which variables are particularly sensitive. So this is not that different, Perhaps the only difference between this particular case and the previous case was, in the previous case, they were looking at cracking and faulting. So they were looking at the product, at the number which comes out of the transfer function. In this case, they actually looked at bottom up and top down fatigue damage. So they stuck to the mechanistic aspect of it. They didn't go into the empirical calculation after that. There are some merits, there are actually many merits to doing that, but it's not relevant for today's lecture. So let me not go into that. They also found, for example, the coefficient of thermal expansion, COTE. That is a very, very important variable. The top-down fatigue cracking is top-down fatigue damage. The top-down fatigue damage is very sensitive to the coefficient of thermal expansion, not so much for bottom-up. So they found this, and they managed to then reduce the number of inputs to a very, very small number of inputs. Just 5 or 6 inputs that they decided were really important. Then what they did was, even then, 5 or 6 inputs, it's still a lot. So what they did is, they actually did a further simplification. If you use pavement ME even for 5 or 6 variables, you would calculate fatigue damage directly. Instead, what pit rigid ME does is, it actually creates a non-linear regression model. So it ran pavement ME for a number of cases, and then instead of running it again, from those number of cases, it created a non-linear regression model. So for example, maybe we talked about joint spacing as being important. So if I write joint spacing here, so what they might have done is, they might have run this for several cases, knowing that it's an important variable. They would have calculated the fatigue damage, and then they just fit it to some non-linear curve. I'll show you the form of the non-linear curve. It's not that simple, but they fit it to a non-linear curve. The advantage for that is, now if you want any other joint spacing, you can simply look up this curve. Running pavement ME can take time. Running those neural networks and running the models, it's a slow process. This, on the other hand, is a relatively fast process. So you can sort of quickly, you get a model, instead of solving the full-fledged computationally heavy model, you get a relatively simple statistical model which can give you an answer quickly. These type of models, this approach of creating a simpler model to replace a more complex and, most importantly, time-consuming model, this is called surrogate modeling. So this paper, basically one thing, it chose to have a limited number of variables, and even for those limited number of variables, it developed a surrogate model. Again, a surrogate model is a simple model which replaces a complicated model, but with comparable accuracy. So they developed a relatively simple nonlinear regression surrogate model which replaces pavement ME. This is an example of what that surrogate model looks like. So I said it's nonlinear regression. As you can see here, there is an exponential function and alpha 1, alpha 2, alpha 3 of some MR. This is actually that FCR. This is the flexural strength. And you got a beta 1 and beta 2. So it's fairly complicated. You have a logarithm of some value. I'm not saying it's an easy regression, but it's some sort of nonlinear regression. It's very easy for a computer to evaluate this as compared to running pavement ME. So the two approaches used by this paper, one, they've limited the inputs to a handful, and then they developed a surrogate model such that you don't even have to run pavement ME anymore. You have a relatively simple model which can run very quickly. Now, this is a pretty good approach, and this is an approach with a lot of emerging research work is doing. Now, what this approach definitely does is, it reduces the design space considerably and speeds up the evaluation. But that still leaves many possibilities. Even 5 or 6 variables is a lot of variables to have to optimize for, such that if you actually want to find a global minima, if you really truly want to find the global minima, the number of computations, maybe it's not trillions, but it's still in the millions. It's a lot. It can actually take days to find such a suitable design. So you really need to have a very good way to do it. I'll tell you 2 ways by which this is done. The MEPDG approach, and this is why I had mentioned for you to remember a little thing in the beginning. The MEPDG approach is actually, they don't do an optimization altogether. What they do is, they start with the trial structure, and the trial structure, most importantly, they have a thickness of the JPCP. So you provide a number of inputs to the trial structure. One of the important inputs is the thickness of the PCC slab. What pavement ME does is that it basically, the update to the trial structure is simply an increment to the thickness of the PCC surface. So they are not doing any optimization. They're not varying a large number of inputs. One input is varied, which is the thickness of the surface. And so this is now an analogous design to ASH 93. After all, ASH 93 is going to give you one output, which is the thickness of the PCC layer. The way pavement ME does its optimization, that's also the only output. Everything else is a fixed input. The only thing it's going to figure out is what is the thickness of the surface layer that you're going to have to use. many design options were missed. I just pointed out previously in the one of the sensitive analysis, it was found the material properties are actually more sensitive variable than the thickness. So that design space is completely being missed by the MEPDG approach. It's a very computationally efficient approach in the sense it's a direct search. Change the thickness, try. Change the thickness, try. You are directly searching for an optimum solution. It's a one univariate, one variable solution. But it misses a lot of possible, a lot of good solutions. So this paper which I'm showing over here, this is from the International Journal of Pavement Engineering. I was not associated with it, but it's from 2011, a good paper. Optimal design of flexible pavements. So it's about flexible pavements, but it equally applies to rigid pavements. Optimal design of flexible pavements using a framework of Dakota and MEPDG. So MEPDG, we already know what that is. Dakota is actually a very sophisticated optimization program. You can download it. It's actually free. You can download it. It's not very easy to install, but it's free. You can download it. It's a very sophisticated, high level, high performance optimization routine. So you can, instead of using this very simplified optimization that MEPDG uses, you can use a more complicated optimization. Here is, for the example, iteration number, and here is the objective function. The objective function is the same one that we have talked about, minimizing the difference between the predicted cracking and the actual cracking. So here is an optimization, here is the iteration number, and here is the value of the objective function. And you see, after a certain number of iterations, more or less reaches a constant value. This is good. So this is a very highly optimized scientific library that can do this multivariate optimization for pavement applications. The problem is, in this paper, they found it can still take days to perform the simulation. So it's exceedingly slow if they use pavement ME, and they also recommended using of a surrogate model. They used a particular surrogate model which is called multivariate adaptive regression spline. It's some sort of a nonlinear regression. So similar to how the first paper created this nonlinear regression, they also ended up creating a nonlinear regression. So what you can clearly see is, although pavement ME is very powerful and it has a lot of interesting computational engines and models, a lot of modern research is going to develop surrogate models because it's a little bit too good in that respect. It's too sophisticated and too time consuming. And so the only way to come up with a really good optimized design is by using a surrogate model. So in terms of optimization, what I showed in this slide, pavement ME just uses a one-shot, it's a direct search method. It doesn't really optimize, it just changes one variable and tells you that. It does not consider the other variables, the other input variables which could have been changed. If you want to consider the other ones, as the other two papers did, you really need a more computationally efficient model. So really, the reason pavement ME uses, despite being so sophisticated, the reason pavement ME uses such a simple optimization method is because anything else is very time consuming, and you really need to come up with these surrogate models if you want to try more sophisticated sorts of optimization. Okay, so that was a little bit researchy, but I think that was a good idea to give you also a little bit of flavor on research in this area. So that concludes all our lectures on MEPDG. So that is the most sophisticated implementation of mechanistic and empirical design today. Not to say there are not others. So we have about 6-7 lectures left in this series. So in the next lecture, lecture 34, I'm going to introduce you the Indian practice of mechanistic empirical design of rigid pavements, and that is IRC 58. So in the next lecture, I'll give you an overview of IRC 58, and subsequent to that, we'll go through many different aspects of IRC 58 and see how in India we design and analyze our rigid pavements. Thank you.